Okay, we have 2 minutes. Okay, just to be clear, I mean, are we starting? I don't think we've been always successful with the code of contact and starting the video timing.
So we're now recording and streaming live on YouTube. So
well, we are already okay.
Yeah.
Because,
so you're welcome to start. I was a little bit quick on the
yeah,
button.
that's fine. Yeah, that's okay. I'm just saying, like, technically, I think we should have done the code of contact.
Yeah.
And then go live, but yeah. All right, so we're ready to start for the 4th day of PKC 2020. Welcome, everyone. We start with the code of contact. As you remember, we are bound by SCR code of contact rules. You have to use your full professional names. If you haven't done that as you entered the Zoom window, it's possible to do that now by renaming yourself using the menu that's on the right. You have to keep your microphone muted at all times, except, of course, when you're asked by a moderator or a host to make a question. And remember that every session is recorded and live streamed on YouTube. So without further ado, the session is Cryptographic Primitives, and Daniela Venturi and Thomas Zacharias are the moderators, and I'm passing the mic to Thomas to start the session.
Thank you, Angelos. So welcome everyone to the session of Cryptographic Primitives. Our first talk would be on witness maps and applications by Subhradeep Chakraborty, Manoj Pragbakaran, and Daniel Weeks, and Subhradeep will give the talk. Subhradeep, whenever you're ready.
Thanks for the introduction, Thomas. So today I'll be talking about witness maps and application. This is a joint work with Manoj and Daniel. So let us just briefly recall ourselves at the setting of non-interactive zero-knowledge proofs in the CRS model. So here a prover who possesses a witness for an NP statement X wants to convince a verifier of the validity of the statement without revealing anything else about the witness, and just by sending a single message. So we want the following properties: completeness, which says that if the prover is honest and the statement is true, the verifier will always be convinced. Soundness says that no efficient cheating prover can convince the verifier if the statement is false. And zero knowledge, which says that no cheating verifier should learn anything else about the witness other than the fact that the statement was true. And this can be formalized using simulators. So since the invention of non-interactive zero-knowledge proofs, many different notions of proof systems have been proposed and used extensively in the cryptographic literature, some of which are NIMI proofs, witness hiding proofs, PCPs, and more efficient proof systems like SNARK, SNARKs, and so on. So against this backdrop of the advances of proof system, we propose yet another notion of a proof system. So in fact, it's a more rudimentary version of a non-interactive zero-knowledge proof, which we call a witness map. So the first notion that I'll present is that of a compact witness map. So in a compact witness map, a CWM essentially deterministically maps witnesses for an NP statement to a much smaller set of representative witness. So let's call capital W to be the set of all valid witnesses corresponding to some NP statement X. And there is a deterministic map which maps this witness set to the set S, and potentially the size of this set S is much smaller than the witness set of X. So we call this, instead of proofs, we call this representative witness, because the W star is essentially an alternate representation of the witness that can be verified using an alternate relation. So in particular, there is a setup. So similar to the NIZIC setup, we use the trusted setup where there is a CRS, and map is a deterministic algorithm which takes a statement and a witness and maps to a representative witness, and check outputs 1 or 0. So as usual, we need completeness and computational soundness, which says that if X is true, the check should output 1, and soundness says that if X is false, check should output 0 with high probability. And now, instead of zero knowledge, we say the compact witness map should satisfy this property of lossiness, which says that the size of this set S should be much smaller than the witness set of W. In particular, the proofs can be efficiently compressed. So now we no longer say that the proofs can in particular be simulated without knowledge of the witness. In particular, each proof leaks some information about the witness, but this leakage is very small. So in particular, when alpha is 0, let's call the size of this set S to be 2 to the alpha. When alpha is 0, we define a notion called unique witness maps. That is, all witnesses mapped to a single canonical representative witness. And in particular, this is equivalent to a deterministic prover and verifier NIWI argument system in the CRS model. We then go ahead and propose yet another notion of a witness map that we call a dual mode witness map, that adds a dual mode property to compact witness map. In particular, there is also a setup which takes as input not only a security parameter, but an injective branch P and outputs a CRS along with a trapdoor, such that if you evaluate this mapping algorithm on the same injective branch, you can extract the witness that was used in creating the proof with the help of this trapdoor TD. So, and we also want the hidden branch property, which says that the CRS should hide this injective branch B. And as I said, extraction. So we assume that there is an efficient algorithm extract that takes the output of the that takes the output of the map and extracts the witness that was used in creating the representative witness. And moreover, we want knowledge soundness, which says that on this injective branch, if the adversary can produce a statement and a proof corresponding to it, then it must know the witness corresponding to the statement in the first place. And now we insist on a stronger property of lossiness, which we call cumulative lossiness, which says that if I evaluate this mapping algorithm on all lossy branches, no matter how many, cumulatively it reveals only alpha bits of information about the witness W. Okay, so as a tool to construct this dual mode witness map, we introduce yet another notion of lossy trapdoor function, which we call a cumulative lossy trapdoor function. So as we all know, a lossy trapdoor function allows for sampling the functions in two different ways. So there is an injective way of sampling the function along with the trapdoor that allows you to compute the function in the reverse direction efficiently. But there is another way of sampling the function, in particular in the lossy way, where the where the range of the function is much smaller than the size of the input domain. Now we ask the following question. Suppose if we evaluate the function in the lossy mode arbitrarily many times on the same input X, what can you say about the information that is revealed by this joint distribution? So if this function is nk lossy, so in particular, it means that it reveals n minus the size of the output domain is n minus k bits, it can be easily seen that if the number of function evaluations is greater than n over n minus k, x can be completely determined.
So Pradeep, have in mind that you are already over time, so if you can wrap up.
Oh, okay. So we propose the notion of alpha cumulative lossiness, which says that no matter how many times you evaluate the function, at most alpha bits of information is revealed about the witness x. So we summarize the main technical contributions of the paper. So we construct a cumulative lossy trapdoor function from DDH and LWE, and we propose the Richer abstraction of all lossy but one trapdoor functions, which we will show how to construct from IO and CLTDF. Then we construct a CWM from IO and punctured signatures, and we show that punctured signatures are equivalent to one-way functions. Then we show that a CWM and this Richer abstraction of trapdoor functions gives you a construction of dual mode witness map. And we also have this interesting connection that this unique witness map implies witness encryption. So this is the newest member of Ophthalmopia and arguably the one with the simplest definition. And finally, as our application to DMWM, we show that combined with hash functions, you can get a deterministic leakage and tamper resilient signature in the bounded leakage and tampering model, and also in the continuous leakage and tampering model. So finally, I want to say that there are some interesting open problems, how to construct CWM from standard assumptions. Also, we don't know if CWMs with superpolynomial image size imply any primitive in Ophthalmopia. And also, can you construct this richer abstraction of cumulative trapdoor functions from standard assumptions? And in particular, since this is a new primitive, can we find more applications of witness maps? So with this, I would want to end my presentation.
So thank you, Supradeep. I see no raised hands.
Maybe can I ask a quick question?
Yes, Daniele.
So, I mean, you said you showed that this unique witness map implies witness encryption. Do you have any witness whether this actually holds also in the opposite direction?
So we actually don't know this. So we only construct UWMs from indistinguishability obfuscation, but we don't know whether it can be constructed from like witness encryption or other primitives in Ophthalmopia. So this is also an interesting open problem.
Okay, thanks.
Yeah, thanks for the question.
Okay,
so may I ask a quick question? Sorry.
Sure. Yeah.
So okay, so your construction relies on non-falsifiable assumptions, yes?
Sorry, say that again.
Your construction relies on non-falsifiable assumptions. I mean, about this knowledge soundness.
So we assume that there is a trapdoor that can extract from the proof.
So your proofs are linear. So basically. Okay, I get it.
Yeah. Thanks.
Okay, so now let's proceed to the second talk of the session, which is efficient reductable signature and application to anonymous credentials by Olivier Sanders. And Olivier, whenever you're ready, you can start.
Okay, everyone see my slide? Okay.
Yes.
Okay, thank you for the introduction. In this short talk, I will present reductable signature and a new efficient construction. I guess that most of you already know digital signature. It's probably one of the main cryptographic primitives that can be used to authenticate digital data, ensuring that not even one bit has been bonified. In practice, you can sign several messages at once, but if you do that, the problem is that you will need to know all the signed messages to check the validity of the signature. And even if you are interested in only one specific subset of messages, you will need to know all of them to run the verification algorithm. So let us consider the following use case when one user gets his attribute certified and just need to prove that, for example, his age is over some threshold, for example, 18. With a solution based on digital signature, the problem is that I will have to send all the signed messages, which is a problem regarding efficiency, but also privacy. there are some solutions, for example, using zero-knowledge proofs that will improve privacy, but this will make efficiency much worse. There are actually a lot of possible solutions in the literature, and I discuss them in the paper. But the problem is that, surprisingly, there is no fully satisfying solution to this problem. More specifically, what we would like to have is a signature scheme for which it is possible to issue constant size signature, for which it should be possible to check the authenticity of any subset of K messages with a constant cost, by sending a constant number of elements. The verification process ideally should only depend on the number of revealed messages. So, for example, in my example, I just need to check the age. So the verification process should only require a constant number of elements, even if I sign the thousands or billions of messages, and would like to be able to prove relations about these messages, not necessarily reveal them. For example, in this example, I actually don't want to reveal my age, but I just want to prove that my age is greater than 18. And finally, I would like to avoid any leakage on the remaining messages. And as I said, there are no fully satisfying solution in the literature. So the starting point of my paper is a primitive called unlinkable reductible signatures that was introduced a few years ago by Chameleon and some other authors. And intuitively, this notion enabled to issue one signature on a set of messages. And then from this signature, you can derive a new signature which is valid on a subset of these messages, on any subset of these messages. And the point is that you can check the validity of this new signature by only knowing the corresponding subset of messages. You don't need to know the other messages. In their paper, Chameleon et al. Proposed a construction, but it is rather inefficient because it contains a very large number of elements. And there are also some problems to prove relations about messages. So the idea of my construction is to propose a new unlinkable reductible signature scheme, which is very efficient. And I used for that a signature scheme that I proposed with David Poincheval a few years ago. It's actually a constant size variant of the Kamenisch-Lizanskaya signature scheme. And this scheme has some interesting feature to construct a reductible signature scheme. The first one is that the messages are involved as exponents in the verification equation, meaning that you can efficiently prove knowledge of them using, for example, the Schnorr's algorithm. This signature can be re-randomized, meaning that you can derive unlinkable variants of a signature. And it is possible to sequentially aggregate these signatures. We will use all these features to construct the reductible signature. In this short talk, I cannot provide all the details of the construction, but intuitively, it works in 3 steps. The first one is simply we can try to aggregate all the irrelevant messages. I will call them the redacted messages in a single element, sigma 1, that will be involved in the verification process. But the problem, if I just do that, is that it's very easy for the adversary to cheat, to create forgeries, because it can aggregate this element, but it can also aggregate some parts of the other messages. In particular,
Olivier, the 5 minutes have passed, so if you can please wrap up the talk.
Okay, so the idea is that to prove that the core idea is that I will not prove that sigma 1 is well-formed, but I will have to prove that sigma 1 does not contain illicit elements, and this can be done very efficiently. So this results in a signature scheme which is very efficient with only 2 group elements for the original signature. Derived signature only contains 4 group elements, no matter the size of the subset I want to prove authenticity. They can be verified efficiently. Right now, the public key is quadratic, but this can be solved actually, this problem, but I cannot say more now. And as I said, the weekend proof relation and the redacted messages are perfectly hidden with this solution. Okay, so thank you.
Thank you, Olivier. So, any questions? Any raised hands? I don't see any.
Maybe a quick question. So what is the reason for the large public key?
To prove that the element sigma1 does not contain illicit elements, I need I will rely on some polynomial relations, and I have to provide many monomials in my public key to do that. But as I said, I'm working on a solution that seems to work that would avoid this problem. But in the current paper, there are still a quadratic public. Thank you for the question.
Any other question? Okay, so thank you, Olivier. Let's proceed to the next talk, which is Constraining and Watermarking PRFs from Milder Assumptions by Chris Pikert and Sina Siehian. And Sina is going to give the talk. Sina, we can't hear you.
Okay. What about now? Can you hear me now?
Yes, now you're fine.
Fabulous. Okay. So this is joined with Chris Pikert. So we will start with reviewing the definition of constraint PRFs. A constraint PRF is a PRF with the ability to generate or delegate constraint keys. So we have the original secret key, the master secret key of the PRF, and we have a user here, and we can generate a constraint key corresponding to a predicate C and give it to this user. We want two properties, correctness and constraint pseudo-randomness. Correctness means that given a constraint key, a user can evaluate the PRF on all points that are authorized by this predicate C. Okay. And we also the other property that we want is constraint pseudo-randomness, which says that if a point is not authorized by this predicate C, then the value of the PRF at this point looks random to the user, even when the user has access to the constraint key. There is a strengthening of the notion of constraint PRFs called private constraint PRFs, which in addition to correctness and constraint pseudo-randomness, we require a third property that says the constraint key hides the predicate C. And these notions, constraint PRFs and private constraint PRFs, they have found various applications. They have found applications in watermarking, deniable encryption, updatable encryption, and etc. And they have been built based on various assumptions. In particular, there are many constructions based on the learning with errors assumption. And this starting with the work of Brakersky and Vakuntanaton, and we have many constructions based on the LWE assumptions. If you look at these constructions, unfortunately, they all need to rely on LWE with sub-exponential modulus, with a modulus that is sub-exponential in the dimension, and this is not a property that we are happy about. This is not something that we are happy about, and we have various reasons to dislike a sub-exponential modulus. For one, sub-exponential modulus means larger parameters, larger public key parameters, larger private key parameters. Whenever you use this, sub-exponential modulus blows up everything. And another reason that we do not like sub-exponential modulus is the quality of the assumption is lower. So as the modulus becomes bigger, the quality of the LWE assumptions degrades. Now, in this work, we build constrained and private constrained PRFs with much smaller modulus. We build private constrained PRFs for polynomial size circuits from LWE with modulus that is only exponential in the depth of the circuit. We build constrained PRFs for logarithmic depth circuits with modulus that is with LWE modulus that is nearly polynomial. And we build private constraint PRFs for inner product predicates based on any Q-homomorphic PRFs. And in particular, if we instantiate the Q-homomorphic PRF with the construction of Banerjee and Picard, then we can get a private constraint PRF for inner product predicates based on LWE with nearly polynomial modulus. And we get our results in a model, a slightly relaxed model for constraint PRFs, but this relaxation is sufficient for almost all of the applications. We will talk about this relaxed model shortly. We also have an additional result. We build private constraint PRFs for TCNFs, for TCNF predicates based on any one-way function. This was also independently observed by Davidson and others. Okay, so in one slide, I will describe our relaxed model and our relaxed model. So the reason that previous works needed sub-exponential modulus is because the correctness requirement in previous works was the correctness requirement is very restrictive. In particular, it requires the value obtained using the constraint key and the original value of the PRF match at almost every point, at almost every authorized point. This is too restrictive, and this causes the LWE modulus to be sub-exponential. Here we relax this correctness requirement to something that we call feasible correctness. And in feasible correctness, we require the original value and the value obtained using constraint key to match at all points that do not depend on the constraint key. And if you think about it, this is a reasonable relaxation, because most of the time, almost every time that you are evaluating a PRF, you are not evaluating on a point that depends on the bit representation of the secret key. And in the paper, we show that if you do this with this relaxation, you can get immensely improve the modulus in LWE, and we also show that you can plug this relaxation into existing constructions, and they work. That's all I have. Thank you.
Thank you, Sina. Any questions for Sina? So I have a question. So in order to get results with no relaxation of correctness, you need some techniques that are fundamentally different, or you can improve on this work, and you see like some promising techniques that you can remove this relaxation.
So right now, I'm not aware of any techniques to remove this relaxation. I think yeah, some fundamental change in the way that we build PRF from lattices are needed.
Oh, I see. I see. Thank you, Sina.
No problem.
Any other questions? Okay. So if we have no questions, let's move to the next talk, and I pass it on to Daniele.
Thanks, Thomas. Okay, for the next talk, the next talk is bringing order to chaos. David Derler, Kai Samelin, and Daniel Zlamanain, and Daniel will give the talk.
Hi, everyone. Thanks for the introduction. So I'm going to talk about Chameleon hashing, and in particular, the different collision-resistant notions associated to Chameleon hashes. Let's start by recalling what the Chameleon hash actually is. So a Chameleon hash is basically a trapdoor collision-resistant hash function. So you have Bob, who is publishing a public key, and then anyone, for instance, Alice, can take a message and then hash the message, which involves some randomness to a fingerprint. And then everybody taking the randomness and the message can check the fingerprint. And if Bob holds the corresponding secret key, then the ability that Bob has is actually that he can, for any arbitrary message of his choice, can come up with a randomness so that hashing this message with the randomness and this public key gives a collision, so gives the same fingerprint. And what you want to have from this primitive clearly is that as long as the secret key is not available, the hash function is still collision resistant. Okay, so this primitive is actually quite frequently used. So in various cryptographic schemes, so one of the more prominent applications probably is lifting non-adaptive signature schemes to adaptive signature schemes. But there are also many other applications. Recently, we also have seen applications of Chameleon hashes in much more complex scenarios like reductible blockchains. So overall, it's a quite useful tool. So the state of the art is basically that there are many definitions out there, and there are many different frameworks out there, and there is no really agreed upon framework, and they all use quite different security notions. And often this is quite of a talk field because they are often made up to exactly fit the application at hand. And the contribution of us is that we want to come up with a comprehensive framework. And due to the shortness of the talk, I just highlight some things. And what I will talk about is the collision-resistant notions, and then briefly sketch how the construction looks like. And for all the other aspects, please have a look at the recorded talk. So basically, collision-resistant means that you don't want to have to find, you don't want to be an adversary be able to find collisions. So the initial notion from Kravchuk and Rabin is basically that of a trapdoor commitment. So the adversary is given the public key and should not be able to come up with a collision for the hash function. So we call it weak because the problem is that as soon as you have seen a single collision for the Chameleon hash, then everything is lost because it might even yield the secret key. That's what's known as key exposure in context of Chameleon hashing. So later, Atenese and others came up with a notion that they called enhanced collision resistance. Here is a little bit stronger because you also give the adversary access to collision finding oracle, where the adversary can get collisions for arbitrary messages of its choice. But what you do here is that you record all the hashes that you have seen, and the winning condition is, beyond the ruling out the trivial condition, is that you do not allow the adversary to ask any collision for the hash that the adversary then outputs. So this means that if you have a single collision seen, that this may allow to find you arbitrary collisions, right? So it seems that this is still a bit weak. Then there is another definition out there, which we call standard collision resistance, which is from Kamenisch and others from 17. So here the adversary is given access to also to collision finding oracle. And what you do here is that you record all the messages. And in the winning condition, you say that the adversary should not be able to come up with collision with a restriction that it does not, is not allowed to question, to ask the message in the forgery to the collision finding oracle. So you could ask for H star, but not for the message that it outputs. And this means that it's still, the hash could still be malleable. And actually we show schemes that such schemes exist, and that might be a problem. And what we basically come up with is a notion that is actually the most natural notion, by giving the adversary full access to collision finding oracle and just ruling out trivial collisions that the adversary could find. So just ruling out that the adversary has not asked for the message in the forgery and the hash in the forgery to the collision finding oracle. And this basically rules out the malleability for the hash and the message simultaneously, and it feels like this is the most natural notion that you want to have from a Chameleon hash. So then we come up with a quite simple engineering construction. And what we do basically is we use a CPA secure public key encryption scheme that's perfectly correct. And the Chameleon hash basically is an encryption of the message under the public key of Bob. And then you attach a non-interactive serial knowledge proof of the statement that either the ciphertext is a valid encryption of the message or that you know the secret key corresponding to the public key. And the verification of the hash is simply checking if the proof is correct. Okay, so that's all that I want to say here in the live session. Thank you for coming to the session, and all the details can be found in the ePrint and in the full talk that's linked on the website. Thanks.
Thanks a lot, Daniel. Are there any questions? So I'll start with one question. So can you actually achieve your notion from weaker assumptions than public encryption?
So actually, we are working on that, and you can achieve it from weaker assumptions. Yes. So you can tweak the construction that you can achieve it from weaker constructions, from weaker primitives.
Which assumptions? Like one-way functions? Or?
Yes.
Any more questions?
I had just one short question. Thanks, Daniel, for a nice talk. So do you have some public parameters for such construction because you have public key, yes?
Yeah, I mean, it depends on the NISIC that you're actually using, right? If you're in the ROM, then no, but if you're in the standard model and you need the CRS, yes.
Okay, I see. So, but you are in the standard, yeah?
You can come up with construction in the standard model or in the ROM. I mean, it depends what you want to have, right? For practical instantiations, you can, for instance, construct it from LGAMAL and Schnorr style NISICs.
Okay, I see. Thank you.
Another quick question. So it seems that you can also extract from those commitments if you know the secret key of the public key. So that kind of is that used in applications or that you consider?
So you mean that the extraction functionality is used in an application?
Whether it's useful as well. Right? I think you.
We did not really explore it so far.
Okay. Thanks, Daniel. So we can move to the next talk, which is the usefulness of sparsifiable inputs, how to avoid sub-exponential I/O, by Thomas Agricola, Geoffrey Coteau, and Dennis Hofheinz. And Thomas is going to give the talk.
Hi, can you see my slides?
Yes.
Good. Yes, I'll summarize the paper. The usefulness of sparsifiable inputs, or how to avoid sub-exponential I/O. This is joint work with Geoffrey Coteau and Dennis Hofheinz. Okay, first we'll start with what is indistinguishability obfuscation. It's a method to transform a program into an unintelligible one with the same functionality. So you can see it as a compiler that takes a program and makes this program code unintelligible in a certain sense. I/O is extremely powerful. We can get almost anything we can think of from it, and maybe some additional mild assumption like one-way functions. But actually, many of these applications require a sub-exponential loss relative to I/O. And we don't want that, because at the moment, we don't really have plausible I/O candidates based on standard assumptions. So we have several candidates, but none of it is completely based on standard assumptions so far. It's possible that in the end, we end up with a candidate where sub-exponentially secure I/O is much harder to get than polynomially secure I/O. So we want to avoid this sub-exponential loss relative to I/O. A certain subclass of applications that currently require sub-exponentially secure I/O use an abstraction which is called probabilistic I/O. And that's the subclass we want to improve in this paper. Actually, we believe that some sort of exponential assumption is inherent for probabilistic I/O. So we cannot really avoid the sub-exponentiality entirely, but we can try to push it away from this novel and maybe shaky I/O assumption to something which is more standard and more well analyzed, such as DDH. Okay, maybe we first start with what is probabilistic I/O and why is it so hard to get? Standard I/O guarantees that if we have two programs, deterministic programs, P1 and P2, that behave exactly identically on all inputs, so to say functionally equivalent. Only then I/O guarantees that the obfuscations of these programs are computationally indistinguishable. Probabilistic I/O, on the other hand, offers a much stronger guarantee. If we have two randomized programs, P1 and P2, that only need to behave indistinguishably, then PIO already guarantees that the obfuscations of these programs are also indistinguishable. And that captures an extremely big class of programs. And it's also the reason why PIO is so powerful, but also so hard to get. Okay, building PIO from IO, as was done in Canetti's paper at TCT 2015, they use a one input at a time hybrid argument, which is actually a very standard proof technique, which is used in many of these applications that use have a sub-exponential loss relative to I/O. And the reason is, in every case of interest, the input space is just exponential. And if we do a computational step for all of these inputs, we have an exponential security loss. And we try to avoid that. And our approach is quite natural, actually. We first observe that many of the applications of PIO have a common ground in how they use the obfuscated programs. Namely, the obfuscated programs, they are more often just fed with inputs that come from certain application-dependent distributions with a small input space. These distributions could, for example, be an encryption of the message M for a small message space. And this we can leverage. Namely, we can reduce the number of hybrids for this one input at a time hybrid argument by using an extremely lossy function as introduced by Sentry at Crypto 2016. And namely, we apply this on the random tape of this input distribution and make the input space spacifiable. And then we end up with a polynomial amount of inputs that we actually need to consider. But we are still not completely at a polynomial reduction because we use this extremely lossy function, and those are an exponential assumption. But they can be based on exponential DDH, which is much more standard and well established than this novel I/O assumption. So, yeah. Okay, we formalize this observation with our framework, which we call doubly probabilistic I/O. And in contrast to normal PIO, we need a CRS. We are in the CRS model. And we need to compile this input sampler such that it preprocesses its random coins with the extremely lossy function and makes it spacifiable like that. And also, this input sampler needs to provide a proof that he really did that. The obfuscation then only accepts such spacifiable inputs. And therefore, we restrict the correctness of this obfuscation, but we do not restrict what kind of computations we support. We only restrict how the inputs are generated. Of course, this can be generalized for many sources, and as long as the number of sources remains small enough. Okay, that concludes already my talk. With our framework of doubly probabilistic I/O, we are able to avoid sub-exponential I/O in several contexts. Namely, we avoid sub-exponential I/O in the context of fully homomorphic encryption, spooky encryption, and homomorphic secret sharing. And also there is subsequent work by Döttling and Nishimaki, who use our framework to avoid sub-exponentially secure I/O in the context of universal proxy re-encryption. Okay, thank you for your attention. Any questions?
So I have a quick question.
Thanks. Yes,
so
please.
In your doubly probabilistic I/O framework, you essentially preprocess your input sampler by using this extremely lossy function, and then provide some sort of proof that you did it correctly, right? So you're already in this domain of auxiliary input I/O. And
no, it's not auxiliary input IO in that sense. We just call it auxiliary input. It's just something that the sampler needs to provide, I think.
Okay, and like, what's the kind of proof? I mean, so what is the structure of aux here?
This can be implemented with just a normal NISIC proof. And that's also the reason we need to be in a CRS model. It's just a normal NISIC proof.
I see. Okay, yeah, thanks.
Thanks for the question.
Okay, are there any other questions? Okay, good. So if not, let's move to the last talk of this session, which is linearly homomorphic signatures and scalable mixnets by Chloé Heband, Dong-Hee Fan, and David Pancheval, and Chloé will give a talk.
Okay, thank you for this introduction. Can you hear me and see my slides?
Yes.
Okay, thanks. So a mixnet, is it working? A mixnet is a succession of mixes applied by different mix servers. And because we suppose that at least one mix server will be honest, no one can know the entire permutations that have been applied between the last output and the first input. So the most famous way to construct a mixnet is for a mixnet to randomize each ciphertext, to mixes them, and after to make a proof of permutation on all the ciphertext. So usually the verification phase, the verification cost depends on the number of mixes. And our goal in this paper was to propose a new construction of mixset, so based on linearly homomorphic signatures, and to avoid this dependence of the number of mixes. So the most famous use case of mixnet is the electronic voting scheme, where a voter encrypts his vote and put it in a ballot box. The ballot box is then sealed and mixed. And as no link between a vote and a voter is now possible, we can decrypt all the votes and publish the result. Of course, one needs some guarantee. Only authorized voter must be able to vote. A ballot must be inforgeable, while two ballots in a ballot box must be indistinguishable. And as the ballot box must be sealed, we cannot add, delete, or modify the ballot. And finally, the result must be publicly verifiable. So this implies two security notions of mixnet. So the first one is the soundness. One needs to have the guarantee that the last output is actually a permutation of the first input. While we have also the unlinkability, where we ask that two ciphertexts in an input of a mix server are unlinkable to two ciphertexts in the output of this mix server, so in the input of the next mix server. So the ballot will be composed of informally of the right to vote, a vote, and a signature of the vote. The right to vote will be formalized by a signature of an authority of a public key of a voter. The voter signs with an encryption of a message, and he signs with his secret key the ciphertext. The initial ballot box is just composed of all the ballots. During a mix, we have two steps. The first one is we need to modify each part of a ballot so that one cannot link anymore one ballot to a voter. And the second one, a mix server will choose a permutation and mixes all the ciphertext. So during a mix, the mix server applies the randomization of all the ballots and the permutation. We use linearly homomorphic signature because they can have some interesting property. The most famous are the message homomorphism and the key homomorphism. The first one is that when you have a signature of a message, we ask that you can construct a signature on a message, let's say M up to alpha, while the key homomorphism is when you have a valid signature verifiable with a verification key VK, then you can adapt the signature to have a signature verifiable with a verification key vk up to beta. These two properties are really nice to adapt little sigma in our ballot, but this is not enough for big sigma, so the right to vote, because big sigma represents the right to vote. It must not be possible to construct a new authorized voter from two authorized voters. So the solution is to use linearly homomorphic signature with tags, with one tag per user, and we ask one property that we call tag randomizability, because now tags is in the ballot, one must be able to randomize the tag and adapt big sigma accordingly. So transformation of a ballot, the randomization part is composed of three parts. The first one is that by using a randomizable ciphertext as L-Gamal, we can construct C'(I) randomized ciphertext of the vote. And with the message homomorphism of the signature, we can adapt little sigma. After that, we need to randomize the verification key and adapt big sigma with still the message homomorphism. But now, because we have tags, one need to randomize the tag and adapt big sigma with, this time, the tag randomizability. The third part, the third step, is because we have changed the verification key, one need to still be able to verify little sigma prime. So now we need to adapt little sigma with the key homomorphism. So our paper constructs Mixnet from linearly homomorphic signature schemes, and we need three properties: message homomorphism, key homomorphism, and the most difficult one, tag randomizability. And from them, we construct scalable Mixnet. I didn't explain why we said scalable because of the time. But let's see the paper. Thank you.
Thank you.
If you have questions.
Are there any questions?
So I have a question.
So I have one question. Yes, okay, please.
Okay, thank you. So I wanted to ask, now it has to do with scalability. I wanted to ask about the efficiency of the Mixnets. So what is the computational overhead here? How does it scale with the number of inputs?
So we still depends on the number of ciphertexts. Of course, we cannot avoid that. But so during a mix, one need to have diffie-Hellman proof and a signature of the Mixnet, of the mix server. So we use Brothai to combine all the diffie-Hellman proofs, but it's just 4 elements, two in G1 and 2 in G2, and we use the Bonnet multi-signatures to aggregate all the signature of the mix servers to have only the last verification that is independent of the number of mixes.
I see. Thank you.
Can I ask a related question? So I think you didn't present it in the short presentation. How do you guarantee that all the mixes are actually involved, that not just the last mix mix is the first one? And I think for that you use the multi-signatures, but I'm a bit, for me it is unclear how you can verify the multi-signatures without knowing the inputs of the other mixes, only knowing the output of the last mix. I think that's my biggest.
We just need the initial ballot box and the last one, because we add a second round of on the mix servers. So there is a first round where each mix server mixes the ballot box and produces a signature that they make good mixes. Then after that, all the mix servers are involved in the second round and check that the mixes are still present in the output. In fact, the verification key is almost the previous verification key up to an randomization scalar. Each mixer chooses a scalar, and this represents the permutation, almost. And so at the end, we just need to check that we have the product of all the scalar in the exponent. So it's to avoid that, yeah, the last mixer said, okay, I avoid all the steps and I just take the initial ballot box.
Thanks.
Thanks for your question.
Okay. Thank you. So if there are no more questions, let's thank Chloe again, and let's thank all the speakers of this session. So there are still a few minutes. I mean, if you want to ask any questions about any of the talk of this session, this is a good time to do this.
So I have a question for Thomas. So yeah, you said that the exponential DDH assumption comes from the extremely lossy functions. And that in general, you have this intuition that it's hard to avoid the exponentiality completely from exponential I/O. So this also means that we cannot hope to have extremely lossy functions from milder assumptions.
Actually, what our result doesn't say anything about. Maybe yes, probably that's yes, that fits to our intuition. And but also the paper of Sentry already had some results on why extremely lossy functions can probably not be built from something polynomial, from something standard. We probably need at least something super polynomial, but sub-exponential, but the only construction that's currently known is from exponential DDH.
I see. Thank you.
Thanks for the question.
I have a question to Subhadip. So in these branches, how many branches do you typically assume? Do all applications require exponentially many branches, or?
Yeah, so it's exponentially many branches. So although I've represented it by so I call it branch, but in the paper we call it a tag. So yeah, and the tag space can be exponential. Thanks.
Maybe another question if there's time. So there was this other question about extraction, right? So you only need to be able to extract for a particular tag.
Yes.
And so do you use that to keep the size of the witness small? So if you had to extract for all tags, then presumably the witness would have to be quite big. So is that kind of a feature you use, or?
So we don't directly use this feature. So yeah, so for our application, actually, we want that there is one injective tag, and we should be able to extract on the injective tag. So in particular, in all the literature, we have this complement of the notion where one tag is lossy and all other tags are injective. But for our signature application, we want that the adversary, so suppose we consider selective unforgeability, where the adversary declares the message M star. So we want to set the tag to be this M star so that a forgery at a later point is extractable. But all other signatures are under lossy tags. So since we define this property of cumulative lossiness, so all the signatures should give you not much information about the signing key. So yeah, so for our application, we just need the witness to be extractable only on one tag, but you could potentially generalize it to polynomially many tags as well. And so I see no reason that why the witness size of the witness should increase with the amount of branches you allow it to be extractable.
I think if the witness would be quite small, you would need some kind of non-falsifiable assumption to extract, kind of using a knowledge assumption. Is that what you do, or?
So no, we don't use any knowledge assumption.
Use the trapdoor.
Yes. So potentially maybe if you want extraction on multiple tags, you might need some knowledge assumption. Yes, you're right.
Okay.
Thanks for the question.
So let's thank again all the speakers of this session. And are there any more questions? I see. Sakib, do you have a question? I see your...
Maybe I can ask a quick question about last presentation, sorry. So you had key and ciphertext homomorphism, yes?
Yeah.
So when we have message homomorphism, so basically means that our ciphertext is malleable, yes?
Yeah.
So how we... Okay, so how we...
Our ciphertext is Elgamal ciphertext. So
yeah, exactly. For example, we know that in Elgamal you can change this plain text, I mean. So this doesn't create any problem that you have key homomorphism and message homomorphism, but you need to have non-malleable ciphertext at the end. Do you need any random oracle or something there, or?
Yes, we use a little really simple trick to avoid any combination of Elgamal. So basically, we just want to be able to multiply by an encryption of 1 and to don't modify the vote of someone. And but as we can put any exponentiation of the message of M and the encryption of 1, it can change the message. So to avoid that, we use expanded vector. So instead of signing directly the message and 1, we assign a vector where the first component is just G and the ciphertext. So we'll end the encryption of 1. It's so another signature is at the first position. It's just 1. So when we multiply together, we still check that the first element in the signature is G, so that we are sure that the encryption was not modifying the message. So yeah.
Okay, I get it. Thank you.
Thank you for your question.
Okay, great. So time is up for this session. Let's thank once again all the speakers. And now there are 20 minutes break, and then see you at the next virtual session. Thank you, everyone.